This is a continuation of the previous session. We're still at the session 7/8. The learning outcomes we covered previously were comparing two independent group, comparing two paired groups, and the correlation. What we will cover today is comparing three groups and for independent groups and for dependent groups. So let's start. We have reached last time uh, regarding the كنا خلصنا هون, we finished these. I did not address the R square. I will do that with the linear regression. So we're moving into comparing three independent groups, and the test that is used is the ANOVA, analysis of variance. That's the way of analyzing the data, and the test itself is an F test, and you will see in a second that it comes with 2 degrees of freedom. So we're still using the same data set that we used previously, and we will compare the blood pressure at time 1 according to the drugs. If I'm not mistaken, we have 3 types of drugs. So we start looking at you click on Analyze, Compare Means again, but this time under Compare Means, you're not going to pick one sample, neither the independent. You're going to pick the one-way ANOVA. All right. Under the dependent list, that's your blood pressure. And under factors, you're going to put your meds. Notice there's no need to specify the values like in the independent t-test. If you remember in the independent t-test, we had to specify 1 and 2, for example. Here we just put meds, that's it. However, we're going to do a few things extra. In the contrast, click on, no, actually no. Yes, on the post hoc, please select the Bonferroni Post Hoc. You will see that there are a lot of options for the post hoc, and I will explain what these post hocs in a second. So we're going to go with the Bonferroni. Click Continue. For the options, we're going to pick the descriptive and also the means plot as a way to look at the means. Pick the homogeneity of variance test, and with the Brown, Forsyth, and the Welsh. And I will explain all of that in a minute. No, maybe let me start without this test, and I will repeat with this test in a second. So let's start simple. So I unclick those, take them out for now. We will repeat with them, but let's first do the simple ones. So continue, and I think we're ready to run the test. We click OK. As is the case, you're going to get your output. This is the the syntax that you requested. Okay. Then the first table is your descriptive table. So blood pressure is your outcome variable, and you have group 1, group 2, or medicine 1, medicine 2, medicine 3 as your 3 different medicines. You have the sample size per medicine. So you have 11 people on medicine 1, 16 on medicine 2, and 11 on medicine 3. The average blood pressure for every medicine, and then the standard deviation for every medicine. Also notice the total, you get the total, so the total blood pressure at time 1 and the standard deviation. You also get the standard errors, which we're not going to address here. You get the minimum and the maximum, very obvious what they mean. Also, you're going to get a 95% confidence interval for every one of these groups. Alright, basically what matters for you at this level for this course is just the means and the standard deviations. And you can see that the means are pretty similar to one another, they're not that different. Therefore, you're going to move to your second table. Your second table is your ANOVA, the analysis of variance test, which has the between group and the within group, if you remember from your statistics course. The sum of squares, the degrees of freedom, the mean sum of squares. So as a reminder, the mean sum of squares, nothing but the sum of squares divided by the degrees of freedom to get the mean sum of squares for the between a group. Then the mean sum of square for the within groups. Then you're going to put the between over the within to get the f-test. And that f-test has 2 degrees of freedom, the 2 and the 35s together, to produce the p-value, which comes out to be 0.184. Now the null hypothesis in this setup is that the mu of group 1 is equal to mu of group 2 is equal to mu of group 3. That's the null hypothesis. You might have heard me saying that the alternative hypothesis has to be complementary. Therefore, if your null hypothesis is written such that you have mu group 1 equal mu of group 2 equal mu of group 3, this is your null hypothesis. The alternative hypothesis cannot be only that all three are different, because if all three are different, this is only one scenario of the possibilities of things that's going to happen. So that is not an appropriate null alternative hypothesis. The appropriate way to think about the alternative hypothesis is to say that you have at least one group has a mu that is different from the others. So at least one. This is the alternative hypothesis. Okay? The p-value that we got according to this f is 0.184. Obviously, this is greater than 5%, greater than the 0.05. And therefore, we're going to fail to reject the null hypothesis, and we're going to conclude that these three groups are similar. Okay. Now, in that scenario like this, you do not need the post hoc tests. Post hoc tests are only used when you reject the null hypothesis. So in the scenario where you reject the null hypothesis, where you're going to say they're not equal and therefore there is a difference between the groups, okay, the ANOVA is going to only tell you that there is a difference. So on group 1, on group 2, and group 3, we know they're not equal, but we're not sure where the difference is. Could it be group 1 versus group 2, or group 1 versus group 3, or could it be group 3 versus group 2 versus group 3? You notice here that if we were to do all possible pairwise comparison, that would require of us 3 testing. Yani if I want to know where the difference between these 3 groups, I could run an independent t-test here. That's the first one. Another independent t-test here. That's the second one. And the third independent t-test here. So that would require for me a 3 independent t-test. However, the problem with doing this is that when you're running 3 independent t-tests, the probability of you committing a type 1 error, okay, if you remember type 1 error, this is alpha. This is the probability of you declaring that there is a difference where in fact there's not a difference. The point being, if you run 3 t-tests, your probability of committing a type 1 error is going to be multiplied by 3, because you may commit a type 1 error here, you may commit a type 1 error there, or you may commit a type 1 error here. So instead of ending up with an alpha of 5%, 0.05, actually your real alpha without you realizing is 0.15. And therefore there is a need to correct for this inflation in your alpha. The way to correct for this inflation is within ANOVA, we run the post hoc, and one of which is the Bonferroni that we did. And what the Bonferroni does is that it's going to correct for this alpha. Okay? And the way it corrects for this alpha to make sure that your alpha stays at 5% and not at 15%, you have 2 ways to do that. Either you divide your alpha, and you no longer compare your p-values to 5%, rather you compare your p-values to 0.05 divided by 3, which is complicated because people don't remember to do that. The other option, and this is what actually SPSS does, is that it's going to take your p-value and it's going to multiply it by 3. Okay, and therefore your new p-value produced by the Bonferroni, this one can be compared to the 0.05 without inflating the alpha. Okay, and so going back here, this is what you have. These are your multiple comparison using the Bonferroni, and therefore you have group 1 compared to group 2, group 1 compared to group 3, and then group 2 compared to group 1. This is a repetition of the first one, but this is how SPSS builds things. There are repetitions. Group 2 compares to group 3. That's the third one that is missing. And then you have group 3 versus 1 and group 3 versus 2, and these also are repetitive. The point being, you're going to look at the p-values, the significance, and check if there is anything significant here to be able to determine where the difference is. But mind you, please remember the following. If your ANOVA test right there is not statistically significant, you do not run a multiple comparison tests. It's not appropriate. You stop there. You say, okay, the ANOVA, this is called an omnibus. It's testing the general hypothesis. Is there a difference anywhere? And if this is not statistically significant, then there's no proof that there is a difference anywhere, and therefore you stop. You do not carry on any multiple comparison. However, if this one is statistically significant, then you have reasons to carry the multivariate analysis, and you would look for sorry, you would look for if there's statistical significance here. Again, let me remind you that the difference between doing a Bonferroni versus running all possible independent t-tests is that while you're doing the Bonferroni, you're protecting yourself against the inflation of the type 1 error. And finally, this is the mean plot. It's useful sometimes when you have statistical difference just to see where the difference is. Okay, now if you remember, I said that there is the correction for the equality of variance that I did not run. As a reminder, if you remember when we did the independent t-test, the independent t-test had two options where either the equality of variance is assumed or not assumed. And there was a test there, which was the Levine's test. And according to the Levine test, you go and look at the first row or the second row. Well, the same idea applies to ANOVA. There is the assumption that the variances are equal. Yani variance of drug 1 is equal to the variance of drug 2, which is equal to the variance of drug 3. Now, for these to be variances, I have to square them. Okay? So same idea. We're going to check if we meet the assumption or not. Therefore, I'm going back to my SPSS. Again, rerun the analysis the one way. Everything is the same. I'm not touching anything. Just go under options. And this time we're going to test the homogeneity of variance. In case this is not met, you have two possible corrections, the Brown-Forsyth or the Welsh. It doesn't matter which one you pick. I'm just going to pick both of them. Hopefully you're going to get the same results, like same kind of results in both. So let's continue. Click OK. All right, so again, the first table is the exact same table we had a minute ago. However, what we get here is the test of the homogeneity of variance. Okay, so the test of homogeneity of variance, you have different options. We're going to stick with the first one, which is based on the mean, and you're going to check if it's statistically significant. See, this is the Levine's test, as we've seen in the independent t-test. And it's not statistically significant, which is good. When it's not statistically significant, معناتها I do meet the assumption of equality of variance, and therefore the F that I looked at a minute ago is valid. In the case where the homogeneity of variances were not equal, you can use the correction, which is down here, and it's either the Welsh correction or the Brown-Forsyth, as I said, and these correct for the degrees of freedom. So notice the degrees of freedom here is 2 and 35. This is the standard ANOVA. When you correct for the not equality of variance, the degrees of freedom remains 2 for the between a group. However, within the group they are corrected, and therefore you end up with a different f. So the f used to be 1.776, it's going to be 1.75 and 1.72, and the p-values are corrected. As again, in this scenario, the equality of variance was met, so there is no need for me to look at the Welsh and the Brown's Forsyth, but in case there was a need, I can check their p-values. Okay, so let's do the application. We're going to repeat what we did, but this time we're going to test for blood pressure at time 2. So compare, go to ANOVA, هعمل reset, pick blood pressure at time 2. Again, pick the meds, put them in the factor, and I'm going to request the Bonferroni. As I said, there are a lot of options. The Bonferroni is the most stringent one of all the different ways to correct for the type 1 error. You don't go wrong with the Bonferroni. It's stringent, it's robust. Yani if the Bonferroni detects statistical significance, you're definitely sure the others are going to. But the other way around is not true. Yani the others might detect significant, but not the Bonferroni. Under options, we're going to go with descriptive. Now you know شو معناتها homogeneity of variance, so we're going to tick it. We're going to also tick these two, the means plot as well. Click continue, and let's run the analysis. Okay, now let's look. The numbers 11, 16, 11 did not change. The mean for drug 1 is 136, drug 2 136, and drug 3 is 134. Now notice the standard deviations, 3, 2.9, and 3.2. They're pretty close. If I were to take a guess, I would suspect that the Levine's test for homogeneity of variance is not going to be statistically significant. The next is the test of homogeneity of variance, and sure enough, you notice that they're not statistically significant, which is a good thing. Remember, معناتها the assumption made for my ANOVA are met, and therefore I can just look at my ANOVA. The p-value for the ANOVA is 0.123, so there's no statistical significance, meaning the differences observed here are not statistically significant. These are due to chance only. Okay? كمان there's no need to look at neither the correction, because the Levine's test was not statistically significant, and there's no need to look at the Bonferroni because the omnibus test was not statistically significant. Okay? Last but not least, let's repeat the analysis, but this time for times 3. I put blood pressure times 3, and I run my analysis, and here I'm going to notice that blood pressure at time 1, the average is 127.9. For this is time 3, I'm sorry, the drug 1. Drug 2, this is 128.27, and drug 3 is 123. You can notice that there is a bit of a difference. So I'm expecting to find statistical significance. But to add to that, look at the standard deviation. The standard deviation for the first drug is very, very tiny, whereas the other two ones are similar. And therefore, I'm going to expect that there will be a difference in terms of the variances. So the second table is the test of homogeneity. Sure enough, it's statistically significant. معناتها the ANOVA table is not valid 100%. I need to move to the second one, the corrected ANOVA. And for the corrected ANOVA, whether you use the Welsh or the Brown Forsyth, the p-value is statistically significant. Remember what that means, that the null hypothesis of the three means being equal is rejected, at least one of the mean is different, but I do not know which one it is. To detect which one it is, I have to look at the post hoc Bonferroni, which protects from the inflation of the type 1 error, and right there. So let's look. If you compare drug 1 to drug 2, the p-value is not statistically significant. If you compare drug 1 to drug 3, the p-value is statistically significant. بعد في عنا one comparison يلي هي 2 to 3. If you compare 2 to 3, كمان it's statistically significant. And if we look at the mean plots, this is 1, 2, and 3. Obviously, drug 3 has a blood pressure that is different from drug 1 and drug 2. Drug 1 and drug 2 are different from one another. There's no statistical difference between them. The difference is with drug 3. Drug 3 appears to have a lower blood pressure than these two drugs. And if you go up again to the descriptive table, we were predicting to see something like this. لأنه because the average for the first drug was 127.9, for the second one was 128.9, so there's only a difference of 1. However, for the third drug, the difference was 123.8, a difference of about 4 to 5 units, and that difference is enough to be statistically significant, different from the others. Also to note, you can look at the confidence intervals. Notice how the confidence interval of the third one starts at 122, ends at 125, does not overlap with the confidence intervals of the two others. Whereas the two others, their confidence interval overlap. When confidence intervals overlap, this is an indication of no statistical significance. When they do not overlap, that is an indication of presence of statistical significance. Okay, so we have covered the ANOVA F test. We have compared blood pressure 1, 2, and 3 by meds. We also tried the Bonferroni, and we explained شو معناتها البونفروني. And we also tested for equality of variance using the Levene stats, which again is something that is automatically done in the independent t-test, but not automatically done in the ANOVA. Now to finish, we would like to point out to the following thing. As I said, we're using the ANOVA when we have more than 2 groups, but in fact you can use the ANOVA even if you have 2 groups. So let me clean up the output, and what I'm going to do is I'm going to run an ANOVA by gender. So I'm باخد blood pressure 3 as an example. هحط gender here. There's no need for post hoc because there's only 2 groups, and I will keep the equality of variance, the test. Okay, so let's run that. So these are the descriptive statistics that we have discussed a minute ago. Notice you only have 2 groups, which is normal because I'm comparing genders. And the equality of variance comes out with a p-value that is 0.372. Yani we can assume equality of variance. You get an F test that produces a p-value of 0.293. Okay, let's compare these results to the independent t-test. If I have done an independent t-test, so compare means, go to independent t-test and pick blood pressure at time 3, pick gender. Gender is 1 and 2, I think. Gender 1 and 2. Continue. And I think it's fine. Just click OK. Alright. First of all, I think the descriptive ought to be exactly the same. So Kanana descriptive 127.6, 126.6 with standard deviation 2.75 with 3.0. If we go up to the descriptive in the ANOVA, and I can use the navigation in my output, so click here, 127.6, 127, 2.75, 2.03, exactly the same value. Okay, so I went back to the independent t-test using the navigation. notice the Levine test produced a p-value of 0.372. So let's check what I received in the ANOVA. قلتلكم we used based on the mean, and notice that it's exactly the same p-value for the Levine's test. This is the exact one. Okay. And if I go back to the independent t-test, the p-value for the independent t-test was 2.93. Okay. So if we go back and look at the ANOVA test, 2.93. What I'm trying to say is you get exact same results whether you're doing an independent t-test or an ANOVA for two groups. In fact, the ANOVA is the independent t-test when you have two groups. There's no difference. But people are more used in using the independent t-test when you have two groups. Mind you that in some fields ما بيعرفوا independent t-test. يعني بتلاقوا بيعملوا ANOVA for everything. And we just realized that it's correct. Okay? Alright, so you can actually pick blood pressure 1 and run what I did for blood pressure 3 and compare the results and see that you're going to get the exact same results. Alright, now we're going to do the equivalent of the pair t-test, but for three groups, which is going to be the repeated measures ANOVA. Okay? Alright, so clean the output and go back here, analyze. We're going to go to the linear model. ما في بالcompare means, if you go to the compare means ما في the ANOVA test with blocks. If you remember your 205 كنا نسميهم with blocks. It does not exist. You just have to go to the general linear model, pick the repeated measures. You're going to have this opening up. It's going to ask you to give a name to the factors. So the factor نحن we're going to compare blood pressure at time 1, blood pressure at time 2, and blood pressure of time 3. So what we're really looking at is the time effect on blood pressure. So I'm gonna call it time blood pressure. You have to specify how many levels it has. So we measured it at time 1, time 2, time 3, so it has 3. And you do add. At this instance, you have to click on define, and that now opens the window, and it's going to ask you what are the variables that needs to be considered at repeated measures. So that's blood pressure 1, blood pressure 2, and blood pressure 3. Okay? Now here things can get very complicated very easily, because this is a repeated measures that is a very powerful tool, and as you can see, you can add things to the between and to the covariate, which we'll not be doing in this course. We're only concerned in comparing the average blood pressure at time 1, time 2, time 3. That's it. So we need that, but we also need a little bit of descriptive statistics. So the first thing I'm going to check, so I don't know them by heart, so I'm going to check them one by one to see which ones we're going to use and which we're not going to use. In contrast, let's not use contrast. Plots, it might be a good idea to have plots, and I don't know if we can get that. Let's see. If we put the time maybe on the horizontal, and you add it, and that's it. Just click continue. For the past, aslan we don't have options for that. So go to the EM means, yani estimated marginal means. We're going to put the time effect here, and we want to compare the main effect using again the Bonferroni. Okay, يعني إذا في فرق between, so again we're going to get an overall test if there's a difference between any time point, and we want to know if where the difference exists. Okay, options. In the options, click on descriptives. Okay, and it's enough. Click continue. And okay, I think we're ready now to run the analysis. Just click OK. Okay, so you're going to get a lot of outputs, and let's focus on the ones that we are interested in. So the first one we're interested in is just the descriptive. So blood pressure at time 1 was 140 with a standard deviation of 2.88. It dropped down to 135 with a standard deviation of 3, and then dropped down again to 127 with a standard deviation of 2.9. Notice that the sample size is the same everywhere. Okay, now the next table is the multivariate test. Skip it, don't look at it. The third table is Kiefer-Levine test for the equality of variance, but because it's a repeated measure, there is a higher up test here, which is the test of sphericity. And what you wonder here, or what you're looking for, is for this p-value to be, again, not statistically significant. معناتها the assumption of equality of variance is met, and therefore you can start looking at the the table. And that takes us to this table right here. And notice that this table has the first row reading sphericity assumed, which is based on this test over here. Yani equality of variance is assumed. And just go all the way to the last one, and the p-value is statistically significant, meaning that this is the testing the omnibus test. There is a difference somewhere between the time points, time 1, time 2, time 3, but it doesn't tell us exactly where it is. Okay, to know exactly where the difference is, we have to look at the Bonferroni. The next table is the test for within subject contrast. Just ignore this one. Also ignore this one, and that takes us down to the marginal estimates, which kind of resemble the first table. So أول table كان عندكم المينز والstandard deviation. Here you have the means, the standard error this time, and the confidence interval. And hopefully using the confidence interval, you can start to guess what the multiple testing is going to give you. So notice that the first one, here the confidence interval goes from 126 and it ends at 128. The second one starts at 134 and ends at 136. These do not overlap. And the third one starts at 139 and ends at 141. كمان not overlapping. Meaning that none of the confidence intervals overlap. And therefore, you can guess that probably the blood pressure at time 1 is going to be different from time 2. It's going to be different from time 3. Sure enough, this is our pairwise comparison, the Bonferroni one. It should say Bonferroni somewhere. Anyway, so here's time 1 compares to time 2, and the p-value is statistically significant. Time 1 compares to time 3, and the p-value is statistically significant. And the last one is time 2 compares to time 3, and it's statistically significant. So like we predicted, all the differences, all the time points are statistically different from the others. Come forget this table. As I said, you're going to get a lot of things that you're not going to use in this course. And here's what is happening. The blood pressure starts high and drops and it drops. And every time it's dropping, the difference is statistically significant. So you can conclude that blood pressure at time 1 has dropped statistically significantly to time 2, and then it dropped again from time 2 to time 3 statistically significantly. Okay? Alright, so let's go back and look at the learning objectives. عملنا repeated measures ANOVA. Okay? And مثل ما we compared the independent t-test, we can also compare the pair t-test. So I'm going to do it very simply. So I'm going to repeat my, but instead of having 3, I'm going to have 2. So now it's only 2 time points. And sure enough, time 3 has been removed. I do not need a Bonferroni here. and everything else is, yeah. So we're just going to run this one. So عندي المين for every group, blood pressure 1, blood pressure 2. As I said, you skip the multivariate test, you just go to the, it will not test for sphericity because you only have two groups. It should test for equality of variance, which it's not doing because it's not built to do that. Anyway, you notice that the p-value is very, very tiny, it's statistically significant, and that's it. That's all we care for because we only have two groups. Have we done a pair t-test, analyze, compare means, and pair t-test? The pair t-test, we're running blood pressure 1 my blood pressure 2. Do we need anything in the options? No. Click OK. And if you do that, you will notice that the p-value for the pair t-test between blood pressure 1 and blood pressure 2 is 0.0000, which is exactly what we had a minute ago, right here. Okay. Now, if my memory serves me right, if you take the pair t-test, the 5.868, and you square it, I'm trying, maybe you should be able to find the f-test. So squaring tt, and this is what I'm trying to say, that again, like with the case of the independent groups ANOVA and the independent t-test, which are equivalent when you only have two groups, when you're doing an ANOVA with repeated measures, if you only have two groups and you compare it to the pair t-test, you're going to get the exact same results. And sure enough, there's no testing for equality of variance. I said that it's trying to test for sphericity, which it cannot because you only have two groups. And that is true when you have only two groups. Not only you're not testing for sphericity, but you're also not testing for equality of variance. It's not part of the options in the pair t-test. Okay, so that covers these two learning outcomes, and that's it for this lecture.